We're going to talk about biomass today. All right, so like I said, big things I want you to take away from today. I don't want you to forget about carbon intensity. It is a big category. So what does it mean when we're talking about biomass? That's one of the things we're going to talk about. We're going to talk less about traditional biomass today. I'll just mention a few things about it. We're really going to cover that in our Energy in the Developing World lecture, so look forward to that. But we're going to talk about other aspects of biomass in the commercial sector. And so you guys had some readings and videos. So good, bad, and ugly about biomass. One of the things that's important to think about for biomass and why it's been such an important energy resource for people is that generally speaking, it's available where people are. Not always in the quantity or the form you might want it, but it's there. And so we rely on biomass, and we've relied on biomass for a long time to provide our energy services, right? It's relatively easy to store. I say relatively because it's not as easy to store as like a fossil fuel. Wood will rot, bugs will eat it, things like that. You have to keep it dry. So it is harder to store than that, but a lot of times it's a solid. So in that sense, we can store it. Waste as a fuel is a big part of our biomass category. We're not just talking about, virgin biomass. We're not just talking about trees. We're also talking about waste streams. That's municipal, industrial, agricultural waste, human waste, that kind of stuff. Potential to reduce greenhouse gases, renewable-ish. We'll talk a lot more about that. A lot of diverse characteristics. I say can replace fossil fuels because it is a hydrocarbon just like a fossil fuel. So chemically, biomass can be very similar to our fossil fuels because our fossil fuels are just ancient biomass, right? It's squished biomass. So from a chemical standpoint, we can use it to replace fossil fuels and not just for energy. We look at biomass sometimes for plastics and other materials that we make out of fossil fuels today. We can make them out of biomass too because chemically they can be very similar. Okay, so things to think about. Okay, the bad list is almost as long as the good list. We're still, when we're using biomass for a fuel, we're still burning it. And so air pollution, greenhouse gas emissions, those kind of things are still a challenge when you're using biomass, just like it is for our fossil fuels. Other things that really come into place, and there's a lot of this in here, is land use for biomass. That becomes a big issue, whether it's, like I said, energy crops or wooded places or deforestation, biodiversity, water use, fertilizer use, all those things come into the biomass landscape depending on the biomass we're talking about. And so those are challenges that we need to manage when we're talking about biomass. So big picture, lots of different flavors of biomass. We're going to talk about a few of those flavors. It's very complex and diverse. And I think this is really important. If we're talking about it as renewable, we have to manage it carefully in order for it actually to be sustainable. Because we can deplete our biomass resources faster than they can replenish, right? That's not hard to do. And so I would say we don't have the best track record at doing this sustainably. In theory, you can. You can, cut trees at the same rate that they're regrowing, but I would say our track record isn't the best at that. And so that's a really important aspect on whether it's actually renewable or actually sustainable. Okay, so we put it in our categories. You guys have seen this before, but biomass is here in that semi-renewable category because we have to think about how quickly we're using that resource compared to how quickly it can replenish itself. That's the only way it's actually sustainable. Otherwise, we're depleting it, just like our stock resources. All right, so let's think about some ways to categorize. So when you're thinking about biomass, what are you thinking about in terms of categories, right? Okay, so traditional biomass, which is not what we're going to talk a lot about today, versus commercial biomass. That's two ways of categorizing it. You can think about traditional biomass. People are collecting that for themselves, for their own uses. It's generally not bought and sold. We have estimates on how much we use traditional biomass. The amount of traditional biomass that is being used to meet people's energy needs, the percentage for that is actually going down as people are getting more and more access to other forms of energy, which we'll talk more about in the developing world. And that's really important because it tends to be a lot of hours and work to collect it for very low productivity, and oftentimes it's not in a sustainable way. so that it's not replenishing at the rate people are using it. So reducing this is really important, and of course the health impacts as well. We're mostly going to focus here on commercial biomass, sometimes called modern bioenergy. You're going to hear all these different terms, but that's really just like this commercial biomass aspect. You can think about it in different ways. You can kind of categorize them by whether they're solid, liquid, or gas. The reason this is kind of useful is because we're using it for different stuff. Solid biomass is like a primary energy. We use it for electricity and heat. That's burning wood or other things. Liquid biofuels is almost entirely used for transportation. This is not a primary resource. It's a currency. We have to take a solid and make it into a liquid to use it for transportation. So think of that as just like, for gasoline or hydrogen or whatever, we have to make it from a resource. Biogas, similarly, energy currency, not primary energy. We have to make it from a solid biomass. We can use it for everything we use natural gas for, because it is methane primarily, just like natural gas. And so biogas is just methane from not ancient biomasses, from like today biomass. Okay? So that's one way to think about it. We'll talk about these different categories. Another way to think about it, and I think this is helpful when we're thinking about the sustainability of our biomass, is to put it into categories on whether it's a waste stream or like a forest or crop stream. Because from a carbon intensity, these have very different carbon intensities. In general, waste streams and making use of those are going to be carbon beneficial because we're reducing methane emissions or something like that. And we're using that energy, making it into CO2 rather than just releasing methane. For forests or crops, it gets much muddier. And in a lot of cases, I would say this isn't going to be carbon neutral. At least the way that we're doing it today, because of land use change, because of all the energy inputs that goes into that. And so we'll talk about some case studies on each of those aspects. Okay, so let's start with significance and use. This is just showing, this was an effort quite a few years ago now. I think one of the aspects of reducing biomass use is trying to have more efficient use of that for traditional biomass. This was one effort actually in Darfur to try to reduce people's time for collecting traditional biomass. As we have seen with a lot of these efforts, if you don't really involve the community in how the solutions that you're trying to implement, they don't get used in the way you expect. So for example, these were provided to the area. A lot of times people were just using them alongside their traditional biomass. They were still collecting, kind of spending the same amount of time to collect biomass, but now they could cook faster because they had 2 cook stoves rather than 1, right? And so just thinking about actually getting, feedback and involvement, I think more and more people have realized that that's a really important step when you're trying to go in and help communities have the energy services that they need. Okay, so biomass, what is it? This is the whole list of things that fall under biomass. And so like I said, it is lots of different flavors and very diverse. Everything from our wood and energy crops, agricultural, other waste streams, aquatic biomass, municipal solid waste, all of this falls into biomass, including things like tires. We consider tires biomass once they're a waste stream. So this is why you really have to be thinking about what aspect of biomass you're talking about in order to think about the energy aspect. This is just more like a fun fact. Biomass comes from the sun, right? That's the energy source. It's storing solar energy in a chemical form, right, into a hydrocarbon. That's what our plants are doing at about a 3 to 6% efficiency rate, depending on our plants. That's just kind of how efficient plants are at capturing solar energy. So what do we use mostly? Mostly we use solid biomass. That's our biggest portion of the global supply of biomass is solid. So again, that's using it for electricity or heat purposes, right? We're burning it. You can see we also use waste streams. Some of these waste streams are used like industrial on site. So you can think about paper mills or things like that. They burn their own waste streams for energy sometimes. And then liquid biofuels, that's all transportation. Biogas is anywhere natural gas is used. So again, electricity, heat, other things. So what's it look like? You guys have seen these pie charts before. You can see biomass is pretty small in terms of percentage, both on the world and the US energy stage, somewhere between 3 and 5%. And then electricity, it's still pretty small. 3% on the world stage, 1% for the US. It's not a major energy resource when looking at the commercial picture for biomass. And we'll talk about some of it's growing and some of it's pretty stagnant and not really growing right now. This is another way to kind of look at the biomass use. So think of this as the primary energy. This is upstream. I mean, yeah, this is electricity, but it's still looking at the primary energy that's going into electricity. So if you think about your energy system, right, you have your primary energy and all the stuff you do to it until you get your services. This is showing you services side. So this is total final energy consumption, like what is providing our services after all of the other stuff and the losses. So total final energy consumption doesn't take into account all the upstream losses. And if we're looking at that, then we can put our traditional biomass in here. And you can see in terms of biomass, it's about half and half, traditional and modern. These numbers have come down in terms of traditional biomass. Only a couple years ago, it was 13% of total final energy consumption. So we are seeing, in percentage-wise, less reliance on traditional biomass for energy purposes. And then you can kind of see what the modern bioenergy landscape looks like in terms of industry, buildings, transportation. Those are kind of the bigger sections. But you can see how they're pretty small in terms of the total energy that those different sectors are using. Industry being the biggest, a little over 10%, but agriculture, buildings, it's pretty small percentages, right, on that final service side. So what I'm going to do is I'm going to talk about the two primary things for solid biomass, and then we'll get into liquid biofuels and a little bit about biogas. So let's talk about solid biomass, because remember, that's the biggest part of the pie, is we're using solids for biomass. And we use it for two things. We use it for heat, and we use it for electricity. So this is showing you what we're doing with global bioenergy for heat. So this is, we're burning solid biomass for heat. You can see most of that is in industry. It's kind of the biggest piece. And then you can see kind of like buildings or modern bioenergy. So that's heating purposes and buildings. And then district heating. Important thing to think about is that it's not really a growth area. There's a little bit of growth in this, but there's not a lot of growth happening in using solid biomass for heat. Certainly not very, very fast growth. So slight growth globally. This is what it looks like in terms of what we're using for feedstocks for heat. So more than half of it is solid biomass, and then the other half basically is waste to energy, tiny bit on biogas. So that's kind of the breakdown of bioenergy going into heat. Let's look at electricity, because that's the other big one. Electricity is growing a little bit faster, right, than using biomass for heat. And so you can see kind of the growth rate here. Much of that growth is happening in Asia. China is the fastest growing in the world. As we continue to talk about here, China's growing in all of the above to try to meet its energy needs. And so biomass for electricity is just one of those areas that they're experiencing growth in to meet their growing demand. Again, the biggest wedge is our solid wood and forestry products. So our solid biomass. Agricultural residues are also solid. And then you can see the rest is taken up with municipal solid waste and biogas in terms of making electricity. So this is kind of the mix. The environmental impacts of these are very different, and we'll talk about that some more. But it's very different in terms of an air pollution standpoint using solid wood versus something like biogas. And so that's an important aspect to think about when we're talking about our biomass resources. Okay, so that's globally. We like to bring it from global down to the US. So here's the United States. This is just showing renewable energy. So I already showed you the pie chart, right, showing the biomass is that tiny little sliver. This is just the renewable energy part of the US landscape. And you can see we've been reliant on wood for a long time. Not really any growth happening there. The waste streams, there was some growth kind of in the 80s and 90s. But you can see there's not a lot of growth happening there. Most of the growth has been in biofuels in terms of the energy in the US. And you can see that kind of happened in the early 2000s when we started growing that. Very policy driven. And we'll talk about that policy when we talk about biofuels. But that wouldn't have happened without a lot of policy incentives to drive biofuels into our fuel system. And then you can see other things. So biomass is definitely our largest renewable resource if you consider it renewable. And we'll talk more about that. But if you consider it renewable, it's much larger in terms of its energy input than wind and solar and hydro. But again, these aren't necessarily being used for electricity. These are. So it can be different in the electricity mix. Let's look at it by sector. So this is, again, the United States. We're bringing it down to the United States by sector and how much is biofuels in terms of our renewable energy consumption. So our solids, like our wood and our waste, industrial, commercial, residential, mostly providing heat. Transportation is where our biofuels go. So that's our liquid ones. And then you can kind of see we have some solid and some waste for our electricity mix in terms of our renewables, right? So this is going to be both biogas and solid materials. So pretty small. But in some states, it is more significant than others in terms of the biomass part of the mix. And so this is just showing you, I've got California up there since we're here in California, but this is showing you some of the top states that generate electricity from biomass. California being one of them. You can see Georgia, Alabama, Virginia, Florida, a little bit different mix of where they're using that biomass, but they're getting significant portions from biomass on a state level. You can see in California, we've got almost 90 biomass power plants, waste to energy, but different sources of waste. And we'll talk more about how those happen. But not a huge portion of our electricity mix. I'm going to talk about wood, and then I'm going to talk about animal waste, and then we'll talk about solid waste. And somewhere in there, we'll do the Kahoot. And we'll see if we get to biofuels. We might talk about that in the transportation lecture. So we'll see what's happening. Okay, this is a large bagasse-fired cogeneration plant in Brazil. Does anybody know what bagasse is? Yeah, it's from a sugarcane byproduct. Thank you. So when you are farming sugarcane, bagasse is basically all the leftover stuff. You have to get rid of the leftover stuff before you have a new crop of sugarcane. So sometimes, and a lot of times this was more traditionally, that would just be burned in the field. They would just burn the field to get rid of the bagasse that's left over from collecting your sugarcane. But more and more, especially as Brazil really expanded its ethanol policies and had pressure from international community, I would say, to not burn their fields, they started collecting that bagasse, and then they use it in a cogeneration power plant that can power their ethanol facilities. So they're just burning it for heat and electricity. That's the cogeneration. Instead of burning it in the fields, they're actually collecting it. Sugarcane obviously is one of our resources for ethanol production. So there's kind of two main sources of ethanol. One is sugarcane, one is corn, and we'll talk more about the differences in those two. Brazil, because sugarcane grows really well there, primarily uses sugarcane. In the US, we use corn from the Midwest to make ethanol. And it's very different impacts. Yeah?
When they are burning the bagasse, how are they dealing with the air pollution it is emitting?
Yes, well, just like with burning fossil fuels, it depends on the region's policies. Brazil experiences a lot of bad air pollution, not necessarily just from this, but from using ethanol in vehicles and things like that. Depends on if they require, and I don't know what their standards are now, but it depends on if they require things to capture the particulate matters or if they have measures for that. And I don't know where Brazil's air pollution policies are right now, to be honest. But yes, anytime you burn anything, you have air quality challenges, which is one of the reasons I think it's great if we can move away from burning things for energy. Yeah, great question. And I can talk more about the impacts of using ethanol in their fuel system, which they see the air pollution impacts from that. So one of the questions I often get is like, all right, so we have biomass resources, obviously, here in the United States. We have them globally. how much of our energy could it actually take the place of? Like, could we actually just switch from fossil fuels to biomass? And the answer is no. In terms of the amount of potential biomass that we could use for energy, there was this great study done that took into account all sorts of different land requirements and everything else. The potential comes out to be somewhere around 8% of our current annual energy if we're using all of it. So with the restrictions that we have in place today. So it's not something that is like we're going to replace gasoline with biofuels that we make domestically, for example. We don't have that amount of biomass resource, and you have to think about land competition for things like food and agriculture and other things for biomass. But that doesn't mean that it wouldn't fit into some niches. I think a lot of people are excited about sustainable aviation fuels or something like that would be biomass based. Because that's so hard to do other things. It's really hard to move off of a liquid fuel. And so we'll talk more about that. Some other things to think about for biomass is in terms of its value, it varies a lot. And its energy density varies a lot. And a lot of that is based on how dry it is. You don't want to be burning wet. Because if you think about it, if you're burning like wet wood, you're basically, a lot of the energy is going into vaporizing the water that's in the wood and not to whatever you're trying to heat. So you really need it to be dry tons. And you can see the range in prices. That's going to give you a sense of how worth it is to move it. And so a lot of times you want to use your biomass resource pretty close to where you're making it. That's not always true. We do actually do international trade of wood products, which we'll talk more about in a minute. But it's going to depend on that energy density, how that works out. So in a lot of places, like our ethanol facilities are all right next to our corn fields. We're not moving corn around a lot in order to make it into the ethanol. It works better to just put an ethanol plant nearby. So in terms of wood materials, so we're just talking about wood and wood wastes. You're using it in like heating and electricity in some places, and especially in the Northeast and some places in the Midwest. We still use it a lot for heating homes. There's actually a pretty big portion of that. And then we're using it a lot in terms of the wood residues in terms for energy in like industry. So that's places that are timber companies or, like I said, paper mills, things like that, using it for heat for their own processes. We already saw it's kind of a declining percentage of our mix, but has stayed pretty steady in terms of the amount of wood that we're using for energy. But as our energy use has grown, it's stayed pretty steady. Part of what I'm going to try to do today in lecture is just highlight a few of the different aspects of our biomass system to just get you thinking about it. So for solid biomass, I'm going to highlight the trade between the United States and Europe. So as part of Europe's renewable energy policy, they consider going from fossil fuels to biomass as a carbon beneficial policy. It's been pretty controversial, but that's where they are right now. They've made some tweaks to it, but that's where they still are. So more and more there's been growth in biomass demand for power plants in Europe. And part of feeding that demand has been supply from the southeast primarily of the United States. So the United States has grown actually to be the largest producer and exporter of wood pellets, primarily to Europe, also to other places, from the forests in the southeast. Many of these, this collection is done on private land. So you can see this is just showing a map of federal versus private land. You can see much of the west are forests. A lot of those are national or public forests, but in the southeast, a lot of it is private land, private forests. You guys saw kind of a video of some of the collection that has been going on and the growth that has gone on in the southeast in terms of taking, forest products, making them into wood pellets and sending them to Europe. This is just showing kind of what that growth has looked like in terms of exports and Europe's demand and growth. There's kind of two main players in the US Southeast, Drax Group and Enviva. So I'm going to pick on Enviva a little bit just for a second. This is their website. Displace coal, grow more trees, fight climate change. That's the idea, right? Is that biomass would be less carbon intensive than its fossil fuel counterpart for electricity. Unfortunately, a lot of studies that have looked at this say that biomass is really only carbon neutral on long time scales, decades to 100 years. It can take a decade to a century for a replacement tree to absorb that carbon. And in the meantime, that carbon is contributing to climate change during those decades to 100 years. And so this is where, on the time scales that we're really looking at for climate change, the carbon neutrality really comes into question with these studies. Of course, other impacts, and if you didn't see the video about it, I encourage you to go back and look at the video I assigned. There's all sorts of other impacts when we're taking forests for energy use. So biodiversity, air pollution, ecosystems, whether it's going from a natural forest to monolithic tree farms. We've shown that natural forests and actually even mature forests are better at storing carbon both in the trees and the soil than new trees or monolithic tree farms are. You might think that a tree growing would be absorbing more carbon, but actually those older trees, they've shown that they store more carbon both in their growth and in the soil than some of the new trees do. So it takes a while for that forest to get back to absorbing the same amount of carbon it was. Like I said, it's been controversial. There was a lot of push when Europe was doing its latest revision, and they made some tweaks to it, but I would say that most of the community felt like it didn't go far enough. So, there are kind of competing voices that, they're trying to both make it not too expensive to decarbonize and look at, is it actually having impact? This is kind of where we are in terms of global wood pellet production. The other part of this, like I said, is like these policies tend to run counter to deforestation or reforestation efforts because you're kind of doing the opposite if you're providing wood pellets for part of your energy supply. You can grow, plantations are another way, and people have looked at plantations. You can grow the forest resources that you need. Again, you're taking up land, so it depends on what that land would have been if you weren't doing this. But there's also this kind of same like 40 to 100 year estimate for even a managed forest to absorb that carbon. And so it's that delay, if it even happens in that 40 to 100 years, where that carbon is still contributing to greenhouse gases. So I just kind of summarized the things that we talked about here, things to think about for when we're using woody biomass as an energy resource. I'd be remiss not to mention BECCS. So BECCS is basically biomass energy with carbon capture and storage. This is another aspect that people point to is like, okay, well, what if we were burning that woody biomass and then sequestering the CO2 off of the power plant? Certainly that would lower the carbon intensity of the life cycle of this product. You would still have the other challenges that we talked about, right? If you're talking about deforestation, biodiversity loss, air pollution, other things would still be a challenge, even with this kind of system. Some studies have shown that this would be carbon neutral or carbon negative, and it kind of depends on a lot of factors. So it depends on a lot of factors on where you're getting that biomass and how much of the CO2 you're sequestering. So a few aspects for you to think about. Yes, our biomass is less energy dense than its fossil fuel counterparts, but sometimes by a lot. But when they're talking about the carbon intensity, they normalize it to the energy output. So when they're looking at how much energy are you getting, so they normalize it to that. Like, what is the carbon intensity? When you talk about carbon intensity, it's per energy that you're getting out of that fuel. How renewable it is depends on how we're managing it. That's why we put it in the semi-renewable category. Certainly, we grow corn every year on the same acreage of land, and we'll grow corn again next year, right? In that sense, it's renewable, it is growing, it is absorbing carbon when it's growing. It's just, we have to look at the whole life cycle to see if that's actually beneficial in terms of carbon absorbed versus carbon emitted. And that's where it gets complicated when they're doing that. And so it depends on how you're setting up policies to do that. I would say there's kind of the whole gamut of why in the US. You can think about some of our fuel policies as something that is beneficial for our agricultural, community and businesses. And so they're very big fans of having more markets for their products. It's not necessarily from an environmental or a carbon aspect. So you see those competing things, and those kind of influence the policies around it. Yeah, but that's the complexity I want you guys to take away. So that's solid stuff. Let's talk about animal waste, because I think this is a place that we should be using biomass. And it is beneficial both from an air pollution and a greenhouse gas standpoint, is with our farm wastes and our animal wastes. So this is, sometimes we go to a biodigester at UC Davis. So this is one of our field trips. Let's talk about animal waste. And most of the data I have is from the United States, but you can think these will apply globally depending on what animals different countries have. So in terms of the United States, we have more than 10 billion land animals being raised for food. That's our pigs, our cows, and our chickens, right? So we get a lot of waste from these animals. California alone has, over 1.5 million dairy cows. Dairy cows I am highlighting because they are particularly easy to use, relatively easy to use as a biomass resource. And we'll talk more about that in a second. So you can see that's a lot of biomass. And we have regulations in terms of the air quality from these operations. And so when you're using that waste stream as an energy resource, you're also lowering the smells and the air pollution from it. So it's kind of win-win when you're doing that. Okay, so what does it look like? This is our US methane emissions, right? Because from our poop and our animals, it is methane that is being emitted from these animals. Two big categories. It's coming off of the poop, or this is not really farting. This is mostly burping. And a lot of this is cows burping. So just to think about what cows eat, they eat grass. That's that cellulosic part of the plant that's really hard to break down. That's why they have 4 stomachs and I have to do all this stuff in order to get a tiny bit of energy out of grass. It's hard to do. And so in that process, they burp a lot of methane emissions. And so that's a big source. There are companies and studies that are looking at this because it's not all the same. You can change their feed. They've shown that if they're eating kelp, for example, they burp less. That lowers their methane emissions. It's easier for them to digest. You can change the mix of animals. There's a couple companies Breakthrough is investing in that are looking at not all cows or not all sheep are created the same. Some of them burp less than others. So can we genetically encourage the types of cows that burp less in order to lower methane emissions, right? So there are ways to try to address this. This is really hard from an energy standpoint to capture. We're not going to put little muzzles on the cows and capture their burps or something. This is hard. But we can do things here from an energy standpoint and capture the manure that's coming off of the cows. And so like I said, it's energy. You're converting methane to CO2 if you're using it for energy. So you're offsetting fossil fuels. You're lowering the greenhouse gas warming potential, and you're reducing the air pollution. So the challenge here is this works best when animals are close together. So that's why dairy cows work really well. You have to bring them all together in order to milk them. And so while they're pooping and milking at the same time, you can collect that manure pretty easily. If you have free-range cows, you have free-range pigs, free-range chickens, it's much harder. So this is where factory farms, it's easier to collect their manure, but there's all the other challenges, right? With factory farms. So that makes it much more of a challenge. So much of the ranching, from my state of Texas and West Texas, it's free range. You're not going to follow the cows around all over the place. You only collect them up when you're ready to harvest them for meat. So that makes it much harder to collect that manure. Okay, so what do we do with it? Cleanest option when we take the poop from the animals is to make a biogas. And you can do that in the biodigester, just like I showed you the one that we go through at Davis. These are more, developing world constructions where these are more community-sized biodigesters, because this is an option for cleaner burning. You're still burning a fuel, but cleaner burning than burning solid materials for communities, households, restaurants. This one's actually for a restaurant that they're collecting the waste and making it into a biogas. We do this with a digester. So basically you're taking the feedstock, which is the manure, you're putting it into an anaerobic environment. And that's really important. As low oxygen as you can, because if oxygen's in there, it's just going to oxidize it and it's going to go to CO2. And that's not useful for an energy standpoint. You want it to be methane. And so it's got to be an anaerobic environment where there's no oxygen, and then you're going to get methane out. It's like a lower quality natural gas. I just say lower quality because it's got a little less, on average, it has less methane than you would just get from the natural gas system, right? So you would have to upgrade it to make it pipeline quality, but you could. You could upgrade this to pipeline quality natural gas and just put it into our natural gas system. It's methane coming off your biodigester. And then you've kind of cleaned up the solid stuff. You can use the solid stuff as fertilizer or fish food or other things. It's not smelly after it's gone through this process. So this is kind of what it looks like. This is kind of that little commercial one for like a restaurant. You pour the manure in, you have this system, you have some sort of overflow tank or something that's keeping pressure on that to keep oxygen out. And then you can take your biogas off. The scale of this matters. Bigger scale is better because you can make that biogas kind of more reliably. I had a student that was trying to do work in Rwanda on doing household level biodigesters, and it's hard to have a continuous stream of biogas from a household level system because the biomass that you're adding to it differs each day. You might have more one day, less another day. You might build up enough biogas for a couple days and then not have enough other days. So it really helps to do it at a community scale or larger in order to have a reliable stream of biogas coming off of your system. All right, so we do this in the US. These are the three main ways that we do this in the US. We could do covered lagoon. You can see the guy, he's like standing on a big lagoon of manure, but it's got a plastic cover on it. That's basically a batch process. So you have kind of a rotating lagoon, and you put a bunch of manure in it, you put this plastic over it, you wait for it to digest, you take the gas off. When it's done, take that cover back off, you can get the solid out, and you can kind of rotate that. Horizontal plug flow is another way, and this way you have kind of a long heated tank where you're putting the manure in at one end, and by the time it gets to the other end, it's all done. Right? And so it's kind of a continuous flow, and you're pulling the biogas off of it as it goes through that plug flow digester. And then the one that we visit is more like this complete mix. This is a batch process where you have tanks and you're actually mixing them, putting the manure in, you're mixing them, you're getting all the biogas off of it, and you have several different tanks so you can rotate them. And you can see that's kind of a third, a third, a third. So plug flow, complete mix, and covered lagoon, those are kind of the three main ways that we're doing these kind of digesters in the United States. How much energy can you get? This is just your rule of thumb. A cow is about 100 watts, so you need 10,000 cows for a megawatt of energy. So just thinking about, or megawatt of power. So just thinking about the energy density of these kind of systems. You're usually doing this for more than just energy reasons, right? You usually have air pollution, things that you're trying to meet. And this is one way to get energy and reduce and meet your air pollution standards, air quality standards. So this is what it looks like across the country. The different colors are different types of animals. So green is pigs, red is dairy, blue is cattle. You can see we don't do that a lot. There's a little bit down here, but generally those are free range. It's much harder to use those for energy. And then poultry is in the purple. So that would be, more of those mass facilities for our chickens. So you can kind of see where that's being done. We are doing this more and more. You can see that there's been growth in 2024. It's providing a little bit of our electricity production, because a lot of this is used for electricity. But in talking to the farmers, and hopefully you saw the video about one of the local ones, it takes a lot of upfront capital. And so even for our local dairy farms in California that have pretty strict air quality standards, they usually have to get federal loan, state loan, nonprofits involved, all of these things, because it takes a long time to actually pay back the investment that goes into developing these systems. You don't make a lot of money on electricity or on selling biogas directly. And so there has to be kind of other incentives stacked in order for these investments to make sense for a dairy farm or something like that. Okay, what do we use the biogas for? So this is again showing you for the United States. So I have data. More and more we're using it for basically pipeline quality. That's what this compressed natural gas or pipeline. So basically they're cleaning up the biogas and putting it in with the natural gas system. That's what they're finding to be most cost effective, rather than generating their own electricity, which is kind of what was done traditionally, was generating your own heat or electricity or doing combined cycle. More and more they're just upgrading the quality and putting it into our natural gas system as a way of getting paid for that biogas. Let's talk about waste streams and using those, and then we'll get to biofuels when we talk about transportation. So this is just kind of, this is a picture from Stanford, right? We've got our landfill, we've got our compost, we've got our recycle bins, different types of municipal solid waste. We produce a lot of waste as municipal solid waste. So globally, 2 billion metric tons of municipal solid waste per year. And if we just put that in landfills, it's going to basically be an anaerobic digester and produce methane. And so some of that methane is vented, some of it is flared, very little of it is used for energy purposes. So from a greenhouse gas standpoint, just burying our waste is not just doing that and then venting or flaring the methane is not good for environmental greenhouse gases, climate change, things like that. And it's a lot bigger than we thought, according to some kind of studies that have been done in the past 5 years or so. And you can kind of see where the countries with the largest landfill gas emissions are coming from, at least as far as measurements can tell, right? So US is right up there with China. Okay, so what does our municipal solid waste mix look like? This is our biomaterial for the United States. And you can see a lot of these could be digested into biogas pretty easily. That's our plastics, our yard trimmings, our food, our wood, paper and paperboard. We're burying it, but we could do other things with it, including using it as an energy resource. You could either burn it or make it into a biogas. We generate about 5 pounds of trash per person every day in the US, so we have a lot of municipal solid waste. The energy content of this mix, it takes about 2,000 pounds to be 500 pounds of coal. So just thinking about it from an energy density standpoint. We could do other things with it. This is what we're doing with that garbage. A lot of it goes to landfill. Some of it is combusted directly for energy consumption. We do a little bit of composting and recycling and other food management. So we could be moving the stuff we're putting here into some of those other categories, because you saw what the mix is. And so there have been a lot of efforts that have looked at, about half of what we're putting into our landfill, we could do other things with, which would be more useful. But what's the energy class? Let's talk about the energy aspects of this. There's kind of 3 ways we can use our municipal solid waste as energy. We can burn it directly. We can just take it, our municipal solid waste, burn it, and put it with a steam cycle power plant and make electricity or heat with it. We can use our landfills as these biodigesters, these anaerobic biodigesters, and take that methane off and use it. Or we can do some fancy things called gasification that we don't do because it's expensive and there isn't a lot of demand for that. But I'll talk about it anyway. There are some startups that are looking at that. So those are kind of our options in terms of generating electricity or generating energy from our municipal solid waste. So let's talk about the first one, where we're actually just burning our municipal solid waste. We're doing this less and less in the United States because Generally speaking, it's really bad from an air quality standpoint. There's a whole mix of stuff in our landfill waste, and we're not really doing a bunch of separation before burning it. So you can imagine there's electronics in there, there's like metals, there's all sorts of things. So places where we're doing municipal solid waste direct burning, you often have to get a waiver from the Clean Air Act in order to do it. So some states are willing to do that. They get, or sometimes you can get this waiver, but from an air pollution standpoint, it's not the best usually to just burn our municipal solid waste. Some places you can see, Florida, for example, does this a lot, partly because it's very land restrained in terms of the amount of municipal solid waste that you get. It's often expensive to send your municipal solid waste somewhere else to be buried for you. So like, for example, I live in San Mateo County, and San Mateo County is running out of landfill space. And so one of the ways that they try to manage that and try to reduce the amount of waste going to landfill is they give me a compost bin, a recycle bin, and a trash bin, right? And if I want a bigger trash bin, I have to pay for it, right? And so they're trying to discourage waste that they have to bury. It's expensive to send it to Santa Clara County or somewhere else for somebody else to bury it for them. So in land-constrained places, you'll see more of this municipal solid waste being burned directly for energy with the air pollution impacts from it. This is a little bit more what it looks like globally. So this is shared municipal solid waste that is incinerated for energy recovery in different countries. So you can see Scandinavia and Japan are kind of at the top of the list in terms of they're burning a lot more of their solid waste for energy than a lot of other countries, like here in the US, we're just a little bit over 10%. Okay, the other thing we can do, like I said, is use our landfills as that anaerobic digester. So we bury it. We have to take the methane off of it for safety reasons. So instead of venting it or flaring it, we can use it as an energy resource. And so you can see landfills. This is our latest estimate. There are studies that are saying that that's actually a bigger wedge than that. But even at 16% of our methane emissions, that's significant. So can we, instead of venting or flaring it, use it as an energy resource? We do that mostly for electricity, but more and more for direct use or upgrading into our natural gas pipelines. The challenge can be is your landfill actually only has a limited lifetime. So there's kind of an ideal time frame where it's actually producing a lot of biogas. You can imagine that will decline over time, especially after you complete the landfill. So investing in like your own little power plant or something can be a major investment when you're thinking about the lifetime of the operations of that facility versus the lifetime of the landfill. So you have to kind of consider that. If you can upgrade your gas and just put it into the pipeline, like we can here in the United States, where we have extensive natural gas pipelines, that can be a lower investment in just cleaning up the gas. So we're seeing more and more of that. But you can see we do this all over the place. We do it in Half Moon Bay, their landfill, they make electricity and heat with theirs. So you can see we have, operational projects, candidate landfills. So there's a lot more landfills we could be doing this with that we're not, and that's really just economic and cost barriers to taking advantage of that. That final category I mentioned that we don't really do is gasification. You can take a solid and make it into basically a gas kind of directly through heating that solid. You can do that with coal. You can do that with waste streams. You can make it into, they call it a syngas, but it's basically kind of like, it doesn't have to be natural gas, but it's a hydrocarbon, gaseous hydrocarbon. And then you can do all sorts of things with it. It tends to take a lot of energy to do this, and it's not super efficient. And so I would say this is something we know how to do, but not well enough to do economically. So there are a few companies that are looking at it, but not really commercially or at scale. So that's our municipal solid waste, but I don't want to forget about our sewage, because we create poop just like our animals do, right? We can use that as digesters too. And a lot of times if we're doing a digester with our human waste, you're also, again, lowering your air pollution and your air quality impacts from those waste streams. So this is, if you've ever driven by this is kind of right off the freeway. This is East Bay Municipal Utility District's digester. It is a large wastewater treatment plant right next to the kind of 80 and 880 interchange that would be super smelly if they weren't doing this. But they do have a digester. They have different systems. You can see how big this is. There's some people up there. And they are drawing that gas off and able to use it for energy uses. So just like we do with animals, we can do that with human waste as well. And of course, on campus, we have our Kodaga Resource Recovery Center. That's one of the things they've done in research there is how to use our waste streams for energy purposes. They also look at how do we use it for building materials. You can clean up stuff. There's all sorts of things in terms of how can we use our waste streams as an input to these systems instead of just a waste stream. So Kodaga does that. It does projects and all sorts of these different things. But it isn't licensed as a wastewater treatment plant. So basically the stuff that even the water they clean up and stuff, they have to put back into the waste stream and then it goes to Palo Alto's wastewater treatment plant to be treated again. So they can't just do that. Biofuels transportation part of our biomass system. In the United States, we're using quite a bit of biofuels in our system because of policies that require that usage in our system. Again, it is an energy carrier, not an energy resource. We're taking solids and we're making it into that liquid. So that extra step takes energy in addition to the land use and the other things that we've talked about with our solid materials. And so it's an extra step. We're doing a fermentation. The ethanol that we use in our vehicles in the United States and in places like Brazil, it's the same thing. It's the same thing you would drink in an alcoholic beverage. So we're fermenting sugars to make ethanol. Ethanol is what you would find in beer or wine, things like that. It's a fermentation process. So we know how to do it pretty well, but it does take energy to make that. So what we're going to talk about are the land use impacts, the changes that we see there, and some of the other aspects about trying to continue to have liquid fuels, but are based on biomass rather than fossil fuels. The reason people get excited about biofuels, right, is the idea that they could be carbon neutral, right? That's the reason we started looking at and investing in biofuels, was to decarbonize our fuels. And so the idea, right, is that you grow plants, they absorb CO2, you make them into the fuel, and you burn it and release CO2, and this would be, carbon neutral. You'd be absorbing and releasing that CO2, right? As we've talked about in the biomass lecture, there's a lot more that goes into this. Of course, just even looking at this is making corn ethanol. There's a lot of energy inputs into it that make it not carbon neutral. And then, of course, we looked at things like trees, right? It can take a decade to decades to reabsorb the CO2 that you emit. And so it's not necessarily carbon neutral on the time scales that we care about, even if we can get that tree to regrow. Right? So that's one of the challenges, and I want to keep that in mind about our biofuels. Just a little framing on terminology. Terminology can be really confusing on biofuels because we use all sorts of different things. One of the ways that we talk about biofuels is in generation, although these aren't official terms, they're just kind of used by the industry. First generation would be things that are derived from food crops. So generally speaking, that's worst. Right? We're using the sugars from our food. It's easiest to make into a biofuel, but often the least environmentally advantageous, right? Because we could be eating that instead of making it into a fuel, right? So that's like the corn kernels, the sugar from sugarcane, stuff like that. Second generation would be from non-food biomass. That could be anything from the rest of the plant. We talk about cellulosic. That's like the leaves and the stalk and stuff like that. Much, much harder to break down. There's a reason we don't eat the leaves and the stalk. It's harder to break down. We eat the sugars, right? And so this is harder to do, but often thought about as being more sustainable and less environmentally intensive. Like if we can take waste streams, if you could use paper and make biofuels or something, right? This is a different category. We're not really doing this, certainly not at scale. We're doing it at small scale. Third generation would be biofuels derived from algae. We're not doing this. So it's just like for completeness, really. People are still looking at it, but we're not really doing that much. And then fourth generation is just like, If anybody wants to sell their new way to make a biofuel, they say it's a 4th generation biofuel. Okay. All right. Biofuel policy, like here in the United States, we don't use these terms. We talk about renewable, which is basically 1st generation. We talk about advanced, which is a mix of better 1st generation and 2nd generation. And then we talk about cellulosic, which would be 2nd generation. Okay, so that's how we define it. And I'll talk more about how we define it in US policy. So there's little different categories when we're talking about biofuels. The biofuels we use today are mainly ethanol and biodiesel. And so this is just showing you a chart of the different feedstocks you can get, the conversion processes you can go to get to our biofuels, right? Ethanol, biodiesel are our biggest by far in terms of category. Renewable diesel is growing a lot. We use a lot of renewable diesel in California because it is considered to have a lower life cycle carbon footprint than biodiesel, and it's also easier to use. So let's talk about each one. Ethanol, I already mentioned, it's got a lower energy density. It takes 1.5 gallons of ethanol to be a gallon of gasoline. So you are lowering your fuel economy by putting ethanol in it. We use E10 in the United States because of mandates, right? We also use it as an oxygenate and an octane booster, but we have E10 because our gasoline cars can run on E10 without any modifications. The automakers don't want to go any higher than that because the cars aren't made to operate with ethanol blends any higher than that. So we're kind of stuck at E10 right now. That's ethanol. Biodiesel also has a limit. It's often B20. You can mix up about 20% of that biodiesel into regular diesel and run it in your diesel engine. It's chemically different, and so you can't just swap out the diesel to biodiesel. But renewable diesel is different, and it's what we call a drop-in fuel. And so with a drop-in fuel like renewable diesel, it's fully a hydrocarbon just like diesel. And so you can literally just run your engine off of renewable diesel instead of diesel. And so that's where it's in this different category than biodiesel. Both of them biomass-based. And then you've heard sustainable aviation fuels. We'll talk a little bit more about that. A lot of interest, a lot of investment in that. Really small scale right now. That's making jet fuel out of a biomass-based resource. Okay, so let's look at some charts where we're at. So I mentioned it's ethanol, biodiesel, and then renewable diesel in terms of our fuels. So here's ethanol, biodiesel, and the little bit of growth in renewable diesel we're seeing. Most of the biofuels are both produced and consumed in these 3 areas. US and Brazil definitely lead in ethanol. The EU has more in biodiesel. But this is where the biofuels are happening globally. Looking at US, I said we were dominated by ethanol for sure in terms of our biofuels. This is their ethanol, and then we have some biodiesel, and then you can see we've seen growth in renewable diesel really driven by California. So almost all of this is used in California. And then you can see our sustainable aviation fuels and other fuels, biomethane, things like that in that tiny little sliver. So this is what our landscape looks like in the US. Still a pretty small portion of transportation. So this is just showing you the share of transportation of the places that have the most biofuels. But this is what provides our transportation fuel in the United States. So we're going to talk the rest of the time about biofuels, but just keep in mind it's that little wedge up there at 10%. We're really still very dominated by oil. A few things to know about ethanol. I already told you that it's less energy dense. It's also harder to transport. So ethanol likes to attract water. It can be corrosive. We can't just put it in pipelines. So often we have to add it at the gas station. You have to move the ethanol around separately unless you've upgraded the pipelines. It's not like we can just blend it into our gasoline and move it around the way the gasoline does. And so it gets a little bit more challenging to move around. It also has different characteristics in terms of vapor pressure. So we're at E10, which actually, is not such a bad vapor pressure, but if you get more and more ethanol, you actually get more and more volatile organics that are coming off of your fuel, which isn't good for air pollution. So you may have heard of all the way up to E85. E85, you finally get back to where ethanol is kind of bonding with itself, get a lower vapor pressure, and then even gasoline. That would be a high blend of ethanol. All right, how do we make it? We make it with sugars, right? That's the stuff that we eat. That's the easiest thing. In the US, we make it with corn. In Brazil, they make it with sugarcane because those are the plants that grow in those locations. right? And it's just fermenting. We're making alcohol, right? It's just the same process we make beer. We're just making it for a fuel. That's why they often call it fuel ethanol instead of drinking ethanol. Okay, so we're fermenting corn or sugarcane. You can see that sugarcane, you can get a lot more gallons per acre. So it's usually considered a lower carbon intensity form of ethanol than corn. And so that's why, like in our domestic policy, sugarcane meets a different standard than corn ethanol because of how efficiently you can grow it and make it into ethanol. Okay, so big difference there. Cellulosic, right? This would be second generation. If we could make it from the rest of the plant. Much harder to do. You have to have special enzymes that are able to break down the cellulosic stuff, which is really hard to break down, right? Cows have 4 stomachs to do it, right? It's hard. To get ethanol, we can do this. We've tried to do it at scale. We're pretty much not doing this. It's hard. There's not a lot of push on it right now. I would say it's not a huge area of investment because we've seen this try to scale and it not work. So let's talk more about ethanol. Where is production happening? US and Brazil, we dominate for ethanol, and you can see this huge growth. In the US, that was driven by policy, which I'll talk about in a minute, really drove this growth. This wasn't like market-based or anything. It was policy-driven growth in ethanol in the US. Brazil went to ethanol following the Arab oil embargo. So we put in a lot of policies in place, including our efficiency standard. Brazil was like, we have all this sugarcane, we can make ethanol. Let's just switch our fuels to ethanol and not be so dependent on importing oil. That was for a while. You can see they've kind of gone back to now. I don't have the latest data, but they kind of can do a blend. So the cars are made to operate either kind of all the way to gasoline or a really high blend of ethanol. So they can kind of flex, and they can have a flex fuel depending on market conditions and other things. For the US, we produce ethanol where we grow corn. So generally, you're not moving the corn very far. You're just building a new ethanol production facility near where you're growing the corn. And so you can see kind of the Midwest is where we dominate in terms of our ethanol production, right next to where we're growing the corn. And our corn acreage increased with our policy that required more biofuels in our system. Right? So this orange wedge is our ethanol for fuel use. And you can just see we basically doubled our, almost doubled our corn crop in order to meet the standards. And so this obviously had impacts on land. We saw a lot of conservation easements go to corn. It impacted flooding. It's impacted fertilizer loading into our rivers and things like that because we're just growing more, we're just dedicating more acreage, more fertilizer, more irrigation to corn production for our fuel. Then we saw years where there was this tension between food and fuel and prices. And so really this is very sensitive to drought. It's sensitive to how much corn is available each year, both domestically and globally, because we export a lot of corn and corn products from the United States to other parts of the world. And so there have been times where we've seen a lot of pressure on food staples. And then you usually start to see these articles about like, we're using our food to make fuel when people are starving or not able to afford food, right? So there's definitely this tension that we've seen, especially at times when there's whatever reason, there's a low food crop. Right? So it's one of the challenges with this, using our food resources for biofuels. It also uses a lot of water to make ethanol from corn. So you guys have seen this chart before, but I just want to point out the corn ethanol part. So this is water consumption for extraction and processing of the fuel. So here's corn ethanol. It's very water intensive. This is an exponential scale. And this is for basically growing the feedstock. And so you can see a lot of that water is used in irrigation of the corn. So pretty water intensive. If we could make it from cellulosic, it would be better. We could use waste streams and things like that, but we haven't figured out how to do that. So this is just more information about cellulosic, but it's not really happening at scale. Okay, so that's ethanol. We got E10. We're kind of at E10 in our system right now. Biodiesel, renewable diesel. We have less of a market for diesel in general, but we do use some biodiesel and renewable diesel, mainly driven by policy. Again, these wouldn't be happening except that we have policies about decarbonizing it. I already talked about some of the differences, but so you can refer back to that. But renewable diesel, just remember that's a drop-in fuel. So what does it look like for biodiesel starting there? EU, they have a much bigger market in biodiesel than they do in ethanol. But you can see we still have a pretty big market for biodiesel. We just have a big diesel demand overall. So you can see we're somewhere around 2 billion gallons, but compared to consumption about 6 billion gallons, still pretty small. What does that look like? So we've seen this growth in biodiesel. It's not expected to grow a lot. Renewable diesel, we've seen this huge growth, but predictions are it's going to keep growing, but maybe not at the same rate. But I want to put that in perspective as here's what the expectation for diesel growth overall. Okay, I don't know why I'm not sad about that drop in diesel, but I don't know why they have that. But anyway, it's a very small portion of the overall diesel market that are biofuels. What do we make the biodiesel and renewable diesel out of? It's mainly vegetable oils and animal fats. Different parts of the world depend on different types of oils. In the US, it tends to be soybean oil. You can see Asia and South America, it's a lot of times palm oil. Europe is canola oil. Just different oils for different regions, but you're kind of doing the same process. Of course, we can talk about the different environmental impacts of this. This is just one of them. I'm going to pick on palm oil for a second, which is not just used for fuels, right? We use it for foods as well. So this is a palm oil plantation in Indonesia. So this is what it looked like before the palm oil plantation. This is what it looks like after the palm oil plantation. So it tends to be very monolithic trees, obviously. Often it looks like this. There are studies that said, well, if you could have an understory, that would be better. But habitat loss is a huge problem with some of these palm oil plantations. So highlighting the orangutans here, but other species as well. I'm going to end with talking about our fuel standards in the United States and what's driven that increase in biofuels and what the goals were. So we have what's called the Federal Renewable Fuel Standard, and we're on RFS 2. And we're just kind of extending that. We started with 1 and now we're on 2. This was a policy that was developed with the help of UC Davis. UC Davis actually has a lot on renewable fuels and things like that in some of their policies, and so they were very involved in setting this up. It is meant to move our fuel system to things that have lower life cycle greenhouse gas emissions than the gasoline or diesel they're replacing. That is actually how it's written in the standard. So when we talk about having policies to address greenhouse gases, that's how this standard is written. And so we have these different categories. Like I said, renewable fuel, it's supposed to be 20% better from a life cycle greenhouse gas emission standpoint. Advanced is supposed to be 50%. Biomass-based are supposed to be 50%. And then cellulosic, that would be our second gen, would be 60% better. And what they did is they set standards for how much volume of fuel would have to be met by these biofuels that are supposed to be lower greenhouse gas emissions. Now, we've talked about all the different things. I guess I should mention this about whether they actually are. It depends on the study you look at. So here's a study that said corn ethanol is 24% higher than gasoline. This one said it's 40% lower than gasoline. I looked at all the studies and the range is like ginormous. It depends on a lot of factors and how much you're including land use change and what you thought that land was going to be used for instead. So that's the question on whether it actually is. But corn ethanol only meets that renewable fuel standard in either case. It doesn't meet any of these other categories. So this is what it looked like. These are the targets. The solid lines, are the targets of what it was going to look like. And then the dashed lines are how the EPA had to adjust based on market conditions. And so the biggest change you will see that's different is in that cellulosic biofuel target, the blue. We were going to have this gross and cellulosic fuel, and we never have. We can't get there. And so they've had to adjust it down every year. So I mentioned this already. We're at E10. Every once in a while, a politician will say we need to be at E15, and the automakers will be like, okay, but you're voiding your warranty on your car. So they get into this little battle about it. We used to have more push on E85 vehicles. That was really to get around CAFE standards. We have less of that now. There are other ways that automakers are able to meet their CAFE standards. So I would say there just hasn't been a lot of tension domestically on biofuels lately. California has its own standard. It's called the Low Carbon Fuel Standard. Again, with the idea that their life cycle carbon intensity of our fuels would go down, and they're requiring that it go down over time. And so you can see that black line is how it is right now, but you can see they also do adjustments to it. If they think we're doing better, like there's too much gap between where we are and where the expectation is, they lower the expectation to try to continue to drive down the carbon intensity of our fuels in California. This is what it would look like. So there's a lot going on here, so I'll just describe this for a minute. If this is the carbon intensity of our gasoline, our diesel, I also have compressed natural gas on here. This is our baseline. We have to do better than this. These are the options, right? So here's our corn ethanol. Here's our sugarcane ethanol. This would be cellulosic ethanol, biodiesel, renewable diesel from tallow, from grease, landfill, CNG, right? And how they compare to what they're replacing. So this is where in California, corn ethanol does not meet the standard from California's perspective. Sugarcane ethanol does meet the standard. And so we've had this history where we've been importing sugarcane ethanol from Brazil instead of using corn ethanol from the Midwest in California as part of meeting the standard. And you can think about the transportation, you know, the leakage parts of that, you know. I like to say California's trying, and I'm just glad they're trying. And then we have to adjust when we realize things aren't working like we want. And we don't do this, right? That would be nice, but we don't do cellulosic, right? So this just gives you a sense of what it looks like. So what are we actually doing in California? This is what our biofuels look like in California. We're just at E10, right? We're not really growing that part of our gasoline mixture. Renewable diesel has seen a lot of growth in California. And then of course, the little yellow wedge that I'm excited about is growing as part of decarbonizing our fuels. So I mentioned we used to import ethanol from Brazil mostly to meet California's standard, and then we were exporting corn ethanol to Brazil. We're doing that less now, but for a while we were really doing that, and there's a lot of reasons we're not doing it as much. One is there aren't as many subsidies for ethanol, and two, now we have import tariffs on ethanol. But we still export a lot of ethanol from the United States. A lot of growth in the Netherlands, actually, on ethanol import. Okay, so for biodiesel and renewable diesel, what are we making it with? A lot of it is from industrial byproducts rather than energy crops. So tallow, used cooking oil, this is like corn oil extracted from grains and solubles. So these big categories, a lot of those are from waste streams. It's only this little soy part really that is from an energy crop in terms of making our renewable diesel for California and meeting our standards. So what does renewable diesel look like in California? All the renewable diesel is pretty much going to us in terms of consumption of renewable diesel. So you guys know that we have refineries that are reconfiguring to renewable fuels. That's because we're seeing growth in this market and declines in this market, right? So they're looking at the future and where the growth is. Final thing to say about biofuels, sustainable aviation fuels, definitely getting a lot of attention, but really, really small part of the market right now. And there's questions on whether these would be first generation. Are we going to use energy crops to make sustainable aviation fuels? Is that really sustainable? So some of the places, like the place in Georgia, that's what they're looking at, is making it from corn. So a lot of question on that. Depending on what you make it from really impacts the cost. But jet fuel is way cheaper than pretty much all of the ways you can make a sustainable aviation fuel. So from a market standpoint, it gets challenging. All right, this is just a summary of some of the things we've talked about in terms of concerns for biofuels. I mentioned fertilizer loading. So these are dead zones that we see occur in the Gulf of Mexico because of fertilizer loading in the Mississippi River. We also see these in Chesapeake Bay. There's another challenge of just growing that corn acreage and the amount of fertilizer we tend to use for our corn crops. So just another aspect of our biofuel impacts. All right, that's it for today. Thanks, guys. If you want to learn more about this topic or other energy topics, visit our Stanford Understand Energy Learning Hub for free resources, including signing up for our monthly Energy Spotlight. Don't forget to subscribe to our YouTube channel and tap the notification bell to be notified for our newest content.